Now you have all the basics to start doing probabilistic damage tolerance analysis. Now that you got like all the basic statistics covered. So we're gonna have this presentation before we go into a small break. Some of the things on this presentation were covered on the overview, but we want to repeat them to you in the way you start like getting familiar with the terminology and some of the things that we do on probabilistic damage tolerance analysis. Okay, so let's talk about like what is probabilistic damage tolerance analysis and what considerations do we have when we do PDTA. So one of them is we have an initial flow size. So just as we do traditional damage tolerance analysis, we need to have an initial crack or initial starting flow that will continue growing with the analysis. We have into account material properties. We need to have into account the geometry. Very important, the load. So we need to know the loading history. So based on that load history, we can grow the cracks, but at the same time, we use that load history to compute our extreme value distribution of the loading. And we use that extreme value distribution of the loading to compute what is the probability during the next flight that load will exceed the residual strength. We're going to take a look to that in a second. To talk about the loading, so we have a very nice loading generation capability within SMART. That's the example that we're going to be doing with the GUI. So that's going to be like the second introduction to the GUI before we move into the master curve analysis on the next presentation. Also, we consider inspection reliability and the probability of detection. So that meaning like we use PODs, and we use those PODs to know if we detect or we miss a crack. And we use the information of both. If we detect the crack, so we go and repair it from another distribution. If we miss it, so we continue having that information to compute the probability of failure analysis. And also we have inspection reliability in terms of POI. So that put like some of the human factors into the analysis. We have the repair. So when we, as I mentioned, when we detect a crack, so we always, in the analysis, we go and repair that one. And the main result that we get is the single flight probability of failure at any time during the operation, okay? So Harry already went through this one. So we have a variation on the material data. We can generate the loading, or you can bring your own loading. From the loading spectrum, so we use these two ways. One is to grow the cracks, if you're going to use, for example, hypergrowth, or if you are using NASGRO or AFGRO, and to generate the extreme value distribution that we use to compute our POFs. We have variation in geometry in terms of the initial crack size, crack aspect ratio, hole diameter, hole offset, and all the inspection capabilities that we have within SMART, okay? We can communicate with AFGRO to grow your cracks. Right now, we do this through the command window. This is not available on the GUI yet, but we have also connection to NASGRO version 7.1, and we're working to get the update to 10.1, which was released early last week. We have an internal crack growth, which is the hypergrowth. Again, what we do here is we create a constant amplitude spectrum that is representative of the variable amplitude, and it has some benefits and some cons, okay? So the process, we can get all these analysis very quick. Some of the cons is, for example, you cannot have retardation into the analysis, just to give you an example, okay? So this is like to put in everything in a single can on what we do with probabilistic damage tolerance analysis. One of the things that we wanted to do is to push the envelope and be able to have more realistic physics-based problems, like having into account all the different variation on the problem. So Dr. Milwari already went through this formulation, but let me just one more time to explain to you what we do. We're academics, so we have to show some equations, okay? So when we compute the probability of failure without survival term, that's what is known as the Lincoln formulation. It's the default in SMART. When you run the analysis today using the GUI, you get the Lincoln formulation, which is this one. We have the fundamental on SMART as well, and if you need to get those results out, we can work with you to do those. But let me go into the analysis a little bit. So the probability of failure at any given time is the probability that the max stress, the maximum stress that you're going to see during a single flight will exceed the residual strength of the aircraft. So the maximum load, this is a distribution that is based on the load history of your airplane, and the residual strength is function of your geometry, is function of your crack size is function of your material properties and so on, just as we do the damage tolerance analysis. And then what we can do is we can use the information of the loading and then compute this as an integral of 1 minus the probability that the residual strength on the extreme value distribution, and this x just represents all the different random variables, okay? So just this is the equation that everybody and we are solving to do a single flight probability of failure, and then different variations. You can get the hazard rate, or you can get the cumulative total probability of failure, and use all this information within the analysis. So again, at the end, what is the main result that we want? We want to have the single flight POF without and with the effect of the inspections. And some of the analysts and some of the engineers, they look at the cumulative total probability of failure, and we also output that one as well, okay? A summary of the random variables, Harry already went through that one. We have initial crack size, fracture toughness, extreme value distribution for the maximum load per flight, DADM parameters, correlated normal crack aspect ratio, hole diameter, and so on. What is very important is this is expandable. So if you need an additional random variable that you don't see here, that is important for your analysis, it's very easy for us to work with you and help you to include those into the analysis. You may tell us, as we mentioned at the beginning, oh, my distribution doesn't fit a normal distribution. So we have the option to input almost everything as a tabular input. So you can put like any weird information that you may have there. Or the beautiful example that Nathan put that I think that is very, very important is what happens if you have a manufacturing error that you want to bring into the analysis. So you can have the manufacturing error have it into account on the analysis. So as I mentioned, we have a beautiful capability in SMART that is to be able to compute a spectra or to be able to compute your loads. Some people, you may have your own tools to develop the loading, so you can bring like your min, max, and number of occurrences into the analysis, or you can use like the capabilities that we have in SMART. So if you're working with general aviation, we have a built-in number of exceedance curves. This came from the AC2313A that were developed from NASA during the early 60s. So we have those into the code, and those are probabilistics. Also, you have the option, like I have my own exceedances for this fighter that I'm working on. You can bring those exceedances into the analysis, and SMART is going to use the traditional methods just to find your pairs of max, min, loads, and number of occurrences. You bring the load limit factors for your aircraft. I'm going to talk about these matrices where you can have variation on the flight duration, flight velocity, and the weight of the aircraft, and how you can use this one for mission to have like a different missions, or just to have like your flight on different flight stages. Like I want to spend 25% of the time like on climb, cruise, descent, initial approach. I'm going to show you how to use that. Also, we have different ways that you can randomize the flights and the stresses. Also, you can have a spectrum editing. So for spectrum editing, we have clipping, or we have death band. You say, hey, all these stresses between -5 and 5, they don't produce any significant damage into my analysis. So I want to do death band, just remove all those. So you can do clipping as well, some of those characteristics into the code, okay? And as I mentioned, if you want to have a user-defined, we use the AVGRO format right now. So this is the different exceedance curves. This is for general aviation. But again, as I mentioned, we have a user-defined. The file format is very simple. That you can like to build your own exceedance and bring it into the code. And what is so nice is we allowed a mixed weighted usage. So you say, hey, I have an aircraft that I use 50% on training, and I use 50% on fighting. So you can bring those into the analysis, okay? This is how the exceedance curves look like. So in the y-axis, you have acceleration fraction, which is normalized by your load limit load. And in the y, you have the exceedance curves per nautical mile, okay? So what this is telling me, if I have an acceleration fraction of 1.2, how many times I'm exceeding those per flight. And then we use like the flight velocity, flight duration to convert this y-axis to per flight. So in that way, we can find the number of exceedances per flight at different stress levels. So what we do is we convert this information here into load pairs per flight. This is one of the examples for the loading. So we can have the pre-taxi, we can have the loading during flight, including gauge, maneuver, and ground, air ground. We have the landing and rebound, and then we have the post-taxi. And then we use this information first to compute the EVD, and second to growth the cracks when we do the full analysis using the spectrum. So as I mentioned, SMART uses two different metrics to account for variations in flight length, flight velocity, and weight. Matrix can be described for fleet variation or to describe flight profiles, as I mentioned. This is a complicated example. I'm going to show you a simpler one on the next slide, okay? But what we have is first column, flight time in hours, going from a quarter hour to 2 hours. What percentage of the flight I spend at these different times? And then here we have velocities in VNO, or we have like a weight, okay, based on the 1G stress, and then all these combinations. But let me show you a simpler example because this one is a little bit more complicated. So let's see that you want to have fleet variation, okay? So you have 4 different missions. We just make like these missions up. It can be any mission that is specific to you. You can say what percentage you spend on a check ride, on high speed cruise, what percentage you have on max weight or max range. Then you can have like a different flight duration, maximum takeoff weight, and what is the cruise speed for those different flights. So what we do is we take these different 4 missions and we populate these matrices that we have here. The first matrix is flight time versus VNO percentage speed. So we have our cruise speed, VNO, in knots. And then what you do is I have flights that they were 0.2 of an hour all the way to 3 hours, as I have it here. And then I say this is 40%, 30%, 20%, and 10% of my flights. And then I fly at 80, 85, 87, and 90% of my full time. And then, so from this, let's take this example. From this mission C, that is a duration of 1.1 hours, I fly 1.1 hours, 30% of the time at 87% of the velocity. So that's how you put it together. Very simple. And same with your maximum takeoff weight. So 100% of the time, when I fly 3 hours, 40% of the time, I go like with my full maximum takeoff weight, which is 7,000 pounds. So that's how you organize this information into SMART to have into account different missions. But let's say I don't want to do a mission analysis. I want to do analysis based on my flight profiles. So you say, I have 4 different flight profiles. I have climb, cruise, descent, and approach. What is my velocity during those different segments of my flight, and what percentage of my total flight duration I spent on these different flight stages? So 50% of the time, I'm going to be flight at 160 knots. And then my weight is going to be this one. You see that the weight starts reducing because the fuel consumption. So you can put like all this into account to have different flight profiles, and then bring these different flight profiles into the analysis. How you do it? So you have 2 different flight profiles. So the first one is twin engine or pressurized general usage. You fly for half hour the whole time, and then you can put into account how your weight is and how your velocity is changing and how your weight is reducing based on those flight profiles that we put together, okay? So as I mentioned, from the loading, we take the extreme value distribution. So what we do is, let me get into the theory first. So the maximum wobble, this is maximum wobble. This is not the traditional minimum wobble that you see, for example, to do initial crack size analysis or fatigue analysis. This is the maximum wobble. So Frechet or Gumbel can be written in terms of the generalized EVD, where this parameter zeta will tell us if this is equals to 0, this is a Gumbel, this is greater than 1, this is a Frechet, or a wobble, if this is negative. And given these 3 parameters, so we can put an optimization using maximum likelihood to find from a set of maximum loads, which one fits the analysis that I'm doing, okay? So how do we do this? So we generate the loading, as I just showed you, and you're gonna have these different flight profiles. So this is my flight number 1, flight number 2, all the way to n number of flights. And what we do is we take the maximum load per flight. Why the maximum load per flight? Because from all the different maximum loads that you have, which one is the one that has the maximum probability that it will break your part into two? So it's going to be the maximum, it's going to be the biggest one. So if this load during a flight exceeds the residual strain, it will break the airplane into two, just to put it in some context during this flight. So we don't need to analyze each of the maximum loads. We'll need to take the maximum. So we take the maximum from each flight, and then what we do is we do an optimization subroutine to find, based on this equation, what is the EVD for that loading. So in this case, so we take all the different ones and we find the parameters mu, sigma, and zeta that will tell me like what EVD do I have in there, okay? So let's take a look to the loading example. I will stop here if you have any questions about loading, about EVD. If not, so let's get into a SMART. So we're going to use the same installation example problem that we use. So we have this geometry where we can have the beta parameter for the hole, the beta parameter for the width, the total beta is the multiplication between both. We're going to be using KC to be equals to this value, okay, deterministic 34.8 KSI per times the square root inch. And then we're going to have the initial crack size is going to be a log normal with these parameters, okay? So we have our crack growth and our residual strength. So in a SMART, and I'm going to move to a SMART in a second, you will have like this tab into the loading where you can select what type of usage you're using. Let me open a SMART so we can take a look to that one as well. So I'm going to open a SMART here. And I'm going to load this example, okay? So I can show you in a SMART what we're doing. This example is contained onto the fundamentals of PDTA, loading example problem, basic POF. So I just load this one, okay? And I'm going to go to the loading. And you see that we have the loading populated here. So what I was showing you is we have all the AC23. This is for general aviation options, okay? But also we have the user defined. So you want to bring your own exceedance, you just select this one, and then you can load your file, okay? It asks for the design maneuver load factor, the minimum and the maximum. For the ground stress, this is in KSI. So please take a look that this is KSI, this is not in PSI. Also, you have the average velocity. You can input your average velocity, and then you can have like your exceedance. If you're going to have variation, the default is 12%, okay? There is always variation, and the variation is 12%. If you don't want to have variation on the exceedance, so you check, let me see if I can check. You check here, you can change this value to 0, okay? Or you can change it to 10, 15, 12, whatever you want it to be. And also, if you want to have a user-defined sync rate, you can have like that sync rate to calculate like the landing and rebound loads. And this is where you input your matrices. So let me take a look to the matrices. So for this example, let me go back to my, I'm going to be using like the mission A, B, C, and D that we were using, where we have a 4x4 matrix. So the only thing that I have to do is to translate this into my matrix. So you see I have the flight times hours going from 0.2, 0.9, 1.9, and 3. You just input this one on the first column. Then the percentage of flights, this is in percentage, and it has to add to 100%. So you see that I have 10, 20, 30, 40. If I add all this, the code is going to check that you go for 100%. If this is not equals to 100%, it will give you a warning, okay? Same in this direction. So the percentage of BNO or VMO speed, it has to add to 100%. So I can, for example, say for my flights that they are like a 0.2 hours, which is the 10%, I can say 50% I fly 80% and 50% I fly at 85%. But the main thing is this value has to be equals to 100. Then for the weight, so you can do exactly the same. You can have all your different weights, and then you can have the percentage where you have those weights. So this is how you input those into Smart. Let me go back to Smart, and I will show you those. So I can switch between these two tabs and between these two tabs, so you can see the values, okay? Just make this a little bit bigger so you can see it, okay? So you can have those values in there. So I don't know how I'm doing with time, but let me get it a little bit in 5 minutes. Yeah, I have time. So into the analysis, so we have 3 different tabs. So just to start, I'm just gonna, because I have way more material in the master course, so I'm gonna use these 5 minutes. So I have the output options. This is telling me how often I want my results up to which value. So I want every 1,000 flights all the way to 20,000. You can choose here if you want in flight or in hours, okay? So this is gonna give me my POF results on the POF file from 0, 1,000, 2,000, 3,000, all the way to 20,000 flights. Also, I have growth. So as I mentioned, I'm using a user-defined crack growth, which I can plot. So you can see the crack growth. You can do on semi-log. So if you have some variations at the end, you can see those variations. And then you have your residual strength on the left by fracture toughness, and on the right on the next section yielding. On this case, for this academic example, we put both of the same. And then you can see what is the value that we use for the master curve toughness, the yield strength, and the hours per flight. So here is 1. So the relation between flight and hours is exactly the same one, okay? And then at the end, you have probabilistic. Here I'm using Monte Carlo. Again, I'm having the loading. So with this loading, I'm going to be computing EVD, which is going to be the extreme value distribution that I'm going to be using to compute my POF calculations. I don't have any inspections. I just come here, I run. It's going to do using the 16 threads. You can see here they have 16 threads. It's using, I forgot how many I'm doing. I'm doing 10 million samples, okay? This is using Monte Carlo sampling. We're going to see later in the afternoon, like using AMIS, like how fast and how good these results are. If I go then to the results, so we can see what we are looking for, which is the single flight POF. So you can see when do I reach 10 to the minus 7, which is the maximum risk that many of the agencies are willing to take. So it's around 8,500 flights, okay? So I will need to take some inspection actions around this point here, okay? If you go back to the run, you can go to show, go to the output file, and see what were the EVD values that were computing by Smart when we use that loading. Okay, so you can evaluate the EVD for that loading. Again, what I did is I went to show and export. I went to the data out, and then you can export this file into a TXT if you want. I can also go to show, export, and you can get your POF, and you can export that one on a CSV file that you can easily plot using any tool, okay? This is what I just showed you. After I did the run, you can take a look to the EVD values just by clicking show and export. And this is the single flight POF results without any inspection. We have not covered any inspections, okay? So I have another 3 minutes too. Okay, so when we do residual strength, so we know that from fracture mechanics, we know that fracture toughness is computed by the stress times beta times the square root of pi a. If I come and I do the residual strength, so this is Kc divided by this parameter, beta times the square root of pi a. So this is how we compute the residual strength. So when we compute the probability of failure, so the probability of failure is this red line is the residual strength. So what we're doing is evaluating from this blue distribution, which is the EVD, we're gonna see what is the probability that my load is gonna exceed the residual strength. So what is in yellow is what in orange is what is producing the failure. So you see that the orange starts increasing. So that's why the POF increases. Okay. So that's what we are doing. We're evaluating the residual strength into the POF. That's very important that we have that concept very clear. We are evaluating the EVD, what is the loading that exceeds the residual strength, so that's my probability of failure. So this is, if we are using limit load, this is just a deterministic value, it's just fail or no fail. The inspection, we're going to be talking about the inspection later today. I'm not going to spend too much time, but inspections is affected by 4 different things: the probability of detecting, the probability of inspecting, which is the human factors, the inspection times when I do the inspection, and how well I do my repair after I do that inspection. So in summary, so PDTA qualified the risk by considering variation in initial flow size, material, geometry, usage, and inspection. PDTA tools are very useful to assess, for example, usage severity. Is very important when you are trying to assess in-service issues. So we always use it mostly of the cases when we have like a field failure. We want to see this is just for that and it's just one case or it's a fleet-based case, okay? And PDTA tools incorporate the effects of inspections, as we're going to see this afternoon. So I'm going to stop here.